Good evening, everyone, and welcome to the June meeting of the Ottawa Centre of the Royal Astronomical Society of Canada. We've got a great program for you tonight. We'll have our usual Ottawa Sky segment, followed by Doug Luoma on his experience at last year's solar eclipse. After the break, we'll have Simon Hanmer, who will be giving us his first of a series of talks on the origins of the solar system. And we'll close off with observations and announcements. So these are our new members from last month, Paul Slavy and David Smith. Let's give them a warm welcome. Thus far in 2018, we've had 19 new members. Members in the news. So each year, the Society gives out awards to recognize outstanding members. And this year, one of our Centre's members was awarded the KELAC Award for Astronomy Outreach. The KELAC Award is intended to recognize individual Canadian residents or teams of residents who have made outstanding contribution during a particular time period, either to the public understanding and appreciation of astronomy in Canada, or to informal astronomy education in Canada, and to promote such activities among the members of the sponsoring organizations. The RASC grants one of these awards per year, and this year's winner was Meg Mogden. Congratulations, Mike. That's very well deserved. Okay, and Starfest is coming up. One of our very own members is going to be giving a talk at Starfest. Paul Cloninger will be giving a talk at Starfest titled Catching Ice, A Guide to Imaging Comets. All right, so now we'll do Ottawa Skies. I'll be presenting instead of Dave, who couldn't join us today. So the full moon is on the 20th of June. The summer solstice happening on the 21st of June. Mercury is not visible this month. Venus is visible all month just after sunset. Mars is visible in the early morning and late evening. Jupiter is visible all night. It was just in opposition last month. Saturn visible in the late evening and early morning all month, and at opposition on June 27th. Uranus is visible in the early morning. Neptune visible in the early morning. Is Dave's monthly comic there? All right, let's hope for some clear skies. Oh. All right, you guys can have a few more seconds. Sorry. All right. Okay, up next we have our first presenter of the evening. That's Doug Luoma. As you all may remember, the Great American Eclipse occurred last August. And with it, thousands of observers descended upon many unsuspecting communities all across the U.S. And Doug will be sharing his experience with us. Which one's the... Yeah, that's the slide. That's the laser and that's...
Hello, everyone. Well, many years ago, Karen and my wife and I, let's turn a slide on here. So Karen and I decided if we were ever going to see a total eclipse of the sun, the one to try for would be the one that crossed the U.S. last summer. To ensure we had a memorable experience, even if the eclipse was a bust, because nothing is certain, even though in the high desert here it's very likelihood of clear skies, but we decided to spend 2 weeks in the region. So we flew to Portland, got into our reserved SUV and drove down past Madras, that's how they pronounce it, and ended up just down here, Prineville Reservoir State Park. And from that base camp, then we just headed off to nice little areas that were scenic and geologically interesting, and we were always looking for interesting western species of birds, animals, insects. For the 5 days around the eclipse, we went northward, just north of Madras, right on the center line, or very close to it. There's the town down here, or city, small city. airport, and there's SolarTown right here. That was created with the city of Madras in conjunction with NASA. There was another venue in town, SolarTown, another camping venue, and lots of farms in the area were renting out spaces on their properties. So this photo montage encapsulates the entire trip. It was the best vacation ever. But today's video is only going to be focusing on this one square, our time in SolarTown. Karen and I got along really well with the other people around us. They were all from Oregon, a nearby town. And spent a lot of time chatting, talking about the eclipse, and worrying about the smoke that was visible daily in the sky from local wildfires. The only camera I brought on the trip is this super zoom camera, Panasonic Lumix FZ200. Because of its smaller size sensor, its focal length in the terms of full frame is 25 to 600 millimeters. That's the only thing I needed to even image the sun. I made a little solar filter with some Bader solar film, just to put it on a step-up ring, designed for easy removal when the totality was there. The sun looks white through that filter, so if you do see a shot with the sun in the field and some color anywhere, then that means there was no filter used for that shot. For visually only viewing of the partial stages, I used my PST, Coronado PST. It shows lets you see the chromosphere, which includes a nice little flame-like prominences on the edge of the sun. And it was just thrilling to see those during totality with just your eyes, just my eyes. But I was surprised at how neon pinkish they looked in color, not the deep red that I see in the scope. Karen used her 80 millimeter refractor. And if you see her describe objects in the field, just remember in that scope it's a mirror reversed image. So we followed the advice of many seasoned eclipse goers that we shouldn't spend the time looking through the camera viewfinder during the limited, precious time during totality. So, and I'm glad I did. But I figured if I do a quick, simple video, you know, as the sun's disappearing, just push the play button and maybe change the exposure just a couple of times during the eclipse to see the different parts of the corona, then that would be more than satisfactory. Well, simple video, yes, but I got so excited as the sun was disappearing that I totally forgot to push the shutter release button until there was only 30 seconds left. Besides the visuals, I missed capturing the audio around me, people talking. When just before totality, someone was going, "It's really gonna happen," and as totality happened, and somebody near me over and over was just saying, "Oh my God, oh my God, oh my God," over and over again. Another person near the end of totality, "Look, Becky, look, I've got a tear. It's so beautiful. I got a tear." And you could hear multiple voices looking up and pointing and going, "I can see stars." It was truly an amazing experience. At the end of totality, I got flustered again. I wanted to decrease the exposure to better capture the first little glint of sunlight, the diamond ring effect, as the moon's just moving out of the way of the sun, but I went the wrong way and brightened it again. But I'm glad I focused more on the visual view of the event. I knew theoretically what it would look like, and I don't get impressed easily, but looking at the sun's dynamic corona with just my eyes is the most beautiful, most awe-inspiring sight I've ever seen in my entire life. And I encourage everybody to, try to get a chance to see at least one of them in your lifetime. The view so overwhelmed me that I could swear for those couple of minutes, the size of the disk of the merged moon and sun were about 2 or 3 times their normal size. It's just the impression I had. So I understand that this is a huge file. It's full resolution, 1920 by 1080 pixels. It was about 2.5 gigabytes. So I understand that the movie may have had to be adjusted a bit. So you may not get that full resolution, but enjoy.
think the mountain's getting some light back on.
Yeah.
Oh, prominence is in several places now. Yeah, I can see. Oh, Bailey's Bridge. Diamond Bridge. Woohoo! Time to put the felder on. Where are the glasses going?
I forgot to turn on the video at the first time. So excited. Okay, glasses on. For sure.
Yeah.
Wow.
Yeah. I know, the light's amazing. It pops right in.
The detail in that scope is incredible.
I know, isn't it amazing? It was so neat. At the last minute, I could see 3 provinces.
The parachutists are doing it to totality. They have lights on.
And it was Regulus I saw. It had to have been Regulus. It was too close not to be, and it was in the lower right, which is where it would have been in this scope. So that was so cool. That was so cool. At the last minute, like there was that prominence at 9. At the last minute, there was one at 9, one at 11, and one at 1. I could see 3 prominences at the very last minute.
Affect the view that much at all. That was wonderful.
Yeah, that was great.
Oh, that's great. That was really exciting.
I got sunburned by the concert.
You'll have to close your head, you have your mouth open.
Oh, it's getting close now.
Yeah, just about.
And
I think that's got it.
Yeah.
Yeah. Yeah. That was it. That was neat.
So those singers in that treated us to a little concert the night before the Eclipse, they were some of our neighbors, and some were in a bluegrass band. And they found out that at the retirement residence where I work, I lead the choir among all my other jobs there. And I told them one day for a Canada Day concert, I had changed the lyrics to John Denver's "Take Me Home Country Roads" to make it more about the Ottawa Valley. So when they found that out, they asked me to try to write a song for them about our Eclipse experiences. So here it is. Pardon my non-professional voice. this country's got a really nice window seat. I'm planning and fretting to make sure I'll be set. Narrow path of sun, meet and greet. Narrow path of sun, high and upward, high desert kisses my face. Right near Madras, Central Oregon. It's very hot, dry, and clear, but my fires are so near. I'm hoping the sun cross fingers, hoping the sun. Fellow campers keep it coming from afar, and capitalist lots of farmers fields are up for rent. Stranger become friends, and surely is the trend. All excited about the city, and you bet. Excited about the city, on a big day, the end overhead is nice and clear. The picture has almost begun. Fills the glasses over eyes and look up to the skies. And the fingertips are back in the sun. And the fingertips are back in the sun. In an hour in the sun is almost gobbled up. The suspense keeps building as it should. Cloudy haze starts spreading just when I wake up. So east to sky, the world don't change. The fight east to sky, with the sun slender crescent, now I'm getting action. And the daily light is great to see. I'm taking the rear, distant mountains to see. Shadow is on to me. It's happened. Shadow is on to me. When the final slice of sun is completely covered up, sun and twilight around is mighty cold. I gaze at the sky with unprotected eye. My nose is starting to unfold. My nose will unfold. Though the blinding sun is fully hidden behind the leaves, radiant power I surely can see. Ghostly ribbons of light streaming out into the night, so wondrous like it's hard to believe. Well, how about I do just a cappella for the last verses? So wondrous, it's hard to believe. 3 pink flames flick out at the border of the sun. Shiny planets and distant stars appear. The glory in the sky brings a tear to my eyes. I know that the end will be near too soon. I know that the end will be near. Wish time could stop and freeze this heavenly sight, but it's brightening at the edge of the sun. Yet the moon won't stay, it's relentless on its way. With dazzling points of light, the night is done, it's over. With dazzling points of light, the night is done. Never had 2 minutes go so fast in my life. Applause and cheers erupt from all around. I feel drained and sated, humbled and elated. Totality's effect has been profound on me. Totality's effect is profound. It'll be another hour till full sun reappears. I'm surprised by the numbers that don't stay. Many pack in a rush to beat the traffic crush. Trains are leaving every minute, across the way like clockwork. Leaving from the airport across the way. Now a sunny eclipse will be coming round again. Across the states in 7 years more. Yes, the shadow is back, but it's on a different track. I have to head somewhere in 2024 and hope I get a repeat performance 2024. Thank you very much.
All right, thank you, Doug. That was awesome. That certainly brought back a lot of memories from the Eclipse for me. That was was a great event to see, and I'm very much looking forward to 2024. All right, so up next, Dave Chisholm sent a video in to Chris and I that speaks a little bit to outreach, and it sort of really reminded me of experiences I've had doing outreach events, and sort of that feeling of sharing in somebody's joy the first time that they see the moon or Saturn through the eyepiece. So yeah, why don't we watch the video?
One night I was bored in my apartment and decided to take my telescope out to the sidewalk. The moon was out and I thought, why not? Within a few minutes, people started walking over and asking what this thing was.
Hey, what is that, bro?
It's a telescope. Do you want to check out the moon? Do you want to take a look at the moon?
What is it?
It's the moon.
Where am I supposed to look?
You're supposed to look right here.
Oh, in there.
Yeah. That's where it all started, and it just sort of went from there.
I'm looking at the moon. Hold on real quick. Hold on. Oh my God.
Oh my God.
Oh my God.
Oh my God. I can't believe it.
Oh my God.
Oh my God. No way.
No way. No way. That's the moon?
No way.
Yeah, way.
Oh, you can see the craters. Yeah. That is so cool. Oh,
Get closer, get wider.
Whoa.
What?
What? Look at the edge. I want to see more of it. I know.
Holy.
I've never seen this before.
I've never seen this before like this, man.
Wow, that is intense right there, boy.
Woo! Bro, that look like that's right down the street, man. Man, what you got here, man? That look like that's right down the street.
Yeah, isn't that amazing? It's right.
Is that an actual image of the moon? Is it like a live image?
It's that right there. To be able to see it up close and feel like you could almost reach out and touch it, and that's what makes it real to us.
That is incredible.
I kind of felt like I just landed on the moon.
It makes you realize that we are all on a small little planet, and we all have the same reaction to the universe we live in.
Wow.
Whoa.
Wow.
Wow. Yeah, wow.
I think there's something special about that, something unifying. It's a great reminder that we should look up more often.
Thank you, Dave Chisholm, for putting that in. It certainly made me reflect on the importance of the outreach work that we do in terms of bringing astronomy to other people, to people that haven't had the opportunity or haven't had the interest in it. Great. All right. So we're going to go to the break. We are running a little bit fast today, so we'll take, why don't we take a 20-minute break and reconvene at 8:22. And we'll have Simon Hanmer after the break. All right. So we're going to get going again. Next we have Simon Hanmer giving us his first of a series of talks on the origins of the solar system.
Thanks, Oscar. Yeah, I always had trouble with my name too. I told my mother she should have married Mr. Smith. It would have made it easier for everybody. She didn't think it was that fun. All right, now listen, let's start with a promise. Dr. Luoma is much braver than I am, but I promise I will not sing. He's good, I'm not. All right, see if I can sort of control my light here. It just wants to swing around. Good. Oh, I don't need to turn around anymore. Beautiful. Now, as I've said many times from this podium, it's a great time to be an amateur astronomer, especially if you're interested in our solar system. Now, all of the major national space agencies are heavily invested in studying our astronomical backyard, and some have been at it for the past decade or so, or 2 decades or so. The abundance of observations is sometimes overwhelming. Think Saturn, Mars, Mercury, and Pluto, and that's just the recent headliners. But beyond observing and measuring what's visible to the eye or geophysically detectable, scientists and amateurs today are keen to understand the origins of our solar system, how it started, how it initially evolved. In short, how did it happen? Now, why do we want to know this? Because we know that our solar system started 4.65 to be precise, billion years ago. And because of that, we can't simply observe directly how things happened way back then. We need to take our observations and our measurements of what we see today and stuff them into computer models, see what pops out, and then ask ourselves how realistic those results turn out to be. Now, there's a lot of variables that go into the astrophysical calculations that the models are made of. And little of what comes out from those models turns out to be black and white. There are always different schools of thought with different points of view, and even within a given school, we're commonly told it could be this or it could be that, and in fact, we're not really sure if it's either. So where does this leave us as amateur astronomers? Well, things are looking up. The story as it sits today is getting pretty complicated. But at the same time, some of the gaping holes and confusing gaping holes in earlier, simpler stories are now being filled in. So in short, as the professionals work their way through their increasingly sophisticated models, they are actually making progressively more sense. So from where I stand, I think we've come to the point where it's time for an updated overview of where we are in the science of the early solar system. So I've put together a series of talks, this will be the first, under the banner of rapidly evolving solar system science, because it is evolving rapidly. The idea here is to bring you up to date in an accessible and understandable way on what solar system scientists are currently thinking and talking about. Do I do it that way? Oh, no, that was the pointer. There we go. All right, I can do this. So today I want to start by looking at the origins of the solar system. What do we think we already know? Emphasis on think. What's new? What are the new questions that the planetary astrophysicists are currently asking themselves? So let's start with an overview of what has become the currently leading model developed over the past 15 years or so. Or to put it bluntly, what has come to be the new standard model. In the beginning, there was the solar nebula. It sounds biblical to state it that way, but that's just the fact. A cloud of interstellar gas and dust that collapsed by self-gravitation and began to spin. Now, a spinning, collapsing cloud turns into a spinning accretionary disk, within which a central star, in our case the Sun, and its attendant planets form by accretion of that gas and dust. And it's this business of planetary accretion that is one of the major headaches facing astrophysicists today. The accretionary disk is hotter in the inner part and it's cooler in the outer part, and it's divided by what's called the snow line. Water can exist outside of the snow line, in other words, in the outer part of the disk, but it gets driven outwards in the part of the disk between the snow line itself and the Sun. This is why we get wet gas and ice giant planets in the outer solar system and drier, rocky, or as they're called, terrestrial planets in the inner solar system. Today, what was originally the wet outer accretionary disk now grades further outwards into what's known as the Kuiper Belt. That's this thing here. This is the area here that actually contains everything you think of as the solar system. That would be the sun and the visible planets. Now that Kuiper Belt it's an outer disk that is populated by comets and icy dwarf planets, likely similar to the dwarf planet Pluto. And then finally, what we see today as the planetary zone, I pointed out that would be this thing right there, and the Kuiper Belt, as again, that's this thing here. They're all enclosed in this sphere, an external sphere of comet materials known as the Oort cloud. Now I know of no models of the early solar system that include an Oort cloud, so its origins are going to remain, well, cloudy. I know. But back to our primeval evolutionary approach, our primeval accretionary disk. Somehow, and that's the operative word here because there's a great deal of debate about this, and that's what we're going to be looking at later. Somehow the dust turned into sand and gravel-sized chondrules that you see here of rocky material that clumped together to form pebble-sized objects, that further clumped together to form asteroids and then planetesimals, planetary embryos, and eventually planets, at least according to the classical model. Inspired by the large number of Jupiter-sized planets located in the inner parts of the planetary systems they were detecting outside of our solar system, astrophysicists introduced the concept of giant planet migration into their solar system models. According to what was originally known as the Nice model, Jupiter formed very early and drifted inwards towards the Sun, followed by Saturn. And that would be what's trying to take place here. Notice this date here, 4.5 billion years ago. We're talking about the beginning of the beginning. When Saturn nearly caught up with Jupiter, the pair of gas giants then turned around and began to migrate back outwards again. In a maneuver known as the Grand Tack, the details of this don't really concern us here at this point. We'll look at them in a later talk. What happened to the rocky planets in the inner solar system while all this migration was going on? Well, according to the Nice model, they hadn't even formed at this point. Given that we know that the Earth formed during the first 100 million years of early solar system history, that means that the giant planetary migration occurred very early. Hence again, that box there, 4.5 billion years ago. Now, here's the next big headache confronting planetary astrophysicists. Not much happens in the model for the next 600 million years. There's our original box, 4.5 billion years ago, and the next thing they talk about is happening here at about 3.9 billion. So not much happens in the model for the next 600 million years, and that's a long time to wait without much idea of what's going on, hence the headache. So we wait 600 million years until Jupiter and Saturn have gravitationally pushed outwards into Uranus and Neptune, pushing them out up against the Kuiper Belt. At which point all hell breaks loose as Kuiper Belt materials are stirred up and hurled gravitationally, they don't actually hit each other, it's all gravitational, into the planetary zone of the developing solar system in what is known as the late heavy bombardment, which is supposed to have occurred at around about 3.8 to 3.9 billion years ago, leaving its imprint as the massive impact basins which we still see on Mercury, Mars, and of course, as we saw in the video before the break, on our own moon. Then, in the classical model, after the late heavy bombardment, accretion was pretty much over bar the shouting, and our solar system has subsisted for the past 3.5 billion years as a stable entity. So as you can see, this Nice model and its Grand Tack component, they're pretty much key to understanding how our solar system formed. In fact, without the Grand Tack, it's pretty tough to explain why Mars is so much smaller than Venus and the Earth. it's pretty tough to explain the construction of the main asteroid belt between Mars and Jupiter. And it's pretty difficult to explain the origins of water on Earth. And without the Grand Tack, it's difficult to explain that late heavy bombardment, which is supposed to have occurred as a cataclysmic event at about 3.8, 3.9 billion years ago. So I'm going to propose taking a closer look at what the NICE Grand Tack model is, how it works, and how it produces the effects that make it seemingly indispensable in modern solar system formation theory. But that's a talk all by itself, and that's for another day. Here I want to go back to the beginnings of the accretion story, the first few million years after accretion began. I'd like us to take a look at what planetary physicists, astrophysicists, are saying today about how accretion began, how dust turned into particles. And I want to do this because it's still a major problem. In 2016, I told you we're talking about rapidly evolving solar system science. This is some of the oldest stuff that I'll talk to you about. In 2016, some of the authors of the NICE model and the Grand Tack component published a list of 5 fundamental bottlenecks, I call them headaches, in understanding planet formation. Read their concluding statement cited here in yellow. You can read it for yourselves. It puts the science in perspective. As the Chinese proverb would have it, the science finds itself in interesting times. So today we'll look at just the first 2 headaches. What is the structure and evolution of protoplanetary or accretionary disks? That's this here. And how did the first planetesimals form? Planetesimals just basically means something much smaller than a planet, but probably bigger than a grain of sand. We'll consider them together because they're intimately linked and because there's a great deal of debate and head-scratching, even today, about exactly how you turn dust into planets. So let's start with accretion. According to the classical models, dust in accretionary disk sticks to other dust in that same disk by electrostatic forces. This is the kind of thing you see when you sweep under your bed. While this sounds simple enough, it turns out that dry 1 millimeter size silicate grains, 1 millimeter is about the size of fine sand, and silicate grains, that's just rock-forming minerals made basically of silicon and oxygen. That's what the Earth's crust is mostly made of, and much of the rest of the Earth too, by the way. These dry 1 millimeter silicate grains, they bounce off each other. They don't stick together. And this is known as the bouncing barrier. Although beyond the snow line, in the outer part of the solar system, where water would have existed, or in fact ice would have existed, they bounce at larger sizes, more like decimeter sizes. That's 100 times larger, because they're cushioned by ice which forms around the grains, and that's less rigid than the silicate grains themselves. However, decimeter-sized particles are big enough to be affected by drag from the gas and dust that's still in the accretionary disk. And because of that drag, they lose angular momentum to the gas, they migrate inwards towards the sun, the star, and they speed up. And as they speed up, their collisions become increasingly energetic, and therefore they become disruptive. In other words, they start to break up and decrease in size, which creates a major headache when you're trying to put together accretionary growth. It puts a severe brake on that accretionary growth process. Now, even if these grains managed to avoid disruption and got to meter-sized objects migrate so fast in towards the sun because of that gas drag that they have no time to actually grow by accretion. And this is known as the meter-sized drift barrier. So how do the astrophysical models get around these bouncing and meter-sized barriers? Well, some suggest that ice and dust form fluffy, compressible particles, and hence they avoid the bouncing and the disruption. Okay. But that, as I said, is only applicable beyond the snow line. Others resort to something else. They resort to proposing, this is all theoretical, okay, because they haven't been there to see it. They're proposing clumping in turbulent vortices. A vortex is just something that spins around like this, around a vertical axis. followed by self-gravitation inside that vortex. And they propose this especially for dry materials inside of the snowline. However, the question of vortices is yet another headache for planetary astrophysicists. Do turbulent vortices even exist in an accretionary disk? And if they do, how big must grains be to get caught up in them? It's not just any grains of any old size that'll work in this model. So some suggest that particles drift towards the accretionary disk's midplane. That would be this. They drift from the outer parts of the disk towards the midplane. And there they could generate spontaneous turbulence by forcing the midplane gas to rotate faster than the gas at the disk surface. So gas in, whoa, wrong way, come back. Oh, no. There we go. Gas in the midplane here would be moving faster than gas out near the disk surface, and so you can imagine that sets up all kinds of problems, which then actually turn into turbulence. And this would be presumably by an exchange of angular momentum from the particles which have drifted into the midplane and the gas. So in short, we now have to consider the behavior, and therefore the structure, of the accretionary disk itself in order to pursue our understanding of early particle accretion. We can't just stand there and say, well, we've got grains bouncing off of each other, and somehow a miracle happens, and they grow into pebbles that grow into planets. We now have to look at things at the scale of the accretionary disk itself to understand what sand grains are going to do. And this is going to get a little bit hairy, but bear with me. You will follow. I promise.
Is there a test?
No, absolutely not. Now, I mentioned drag, exchange of angular momentum, migration, drift, several times now. Clearly, they're important for understanding the behavior of the accretionary disk and objects within it. But what exactly do these things mean, and how do they work? Well, it turns out that they're all related to viscosity. The accretionary disk is made of gas. There's also dust in there, and if accretion really gets going, you end up with larger particles as well. And all of these rub up against each other. And this rubbing generates friction. Technically, one would say it's mediated by friction. And the friction is part of what gives the accretionary disk a viscosity. What do we mean by viscosity? Viscosity is simply resistance to flow, or resistance to movement. Think the thickness, if you will, or the stiffness of molasses versus the thickness or the stiffness of water, where we would say that molasses are more viscous than water. Now imagine trying to swim in molasses. Its viscosity exerts a drag on your motion. Well, it turns out that a viscous disk of gas and dust will exert drag on any relatively large body, and that means anything really bigger than my fist, trying to move through it. But orbiting particles in a rotating viscous disk are not the same thing as you trying to swim in a pool of molasses, because the rotating disk and its orbiting contents all have angular momentum. So drag between the accretionary disk and its contained particles leads to an exchange of this angular momentum, whereby particles above a certain size lose angular momentum to the gas and begin to spiral inwards to the sun. The bigger the object, the greater the drag, and the faster the inward motion. Now, you're probably thinking to yourselves, well, how come the planets are still out there? By the time the planets are finished forming, there was no more gas and dust, no more drag. So, okay, all of this sounds kind of complicated, but at least we can understand that the viscosity of the accretionary disk messes with the angular momentum of particles in the disk and causes them to migrate in towards the sun, such that they speed up and now have increasing problems accreting to each other to form larger bodies. Hasn't gotten us very far, has it? But now there's an added complication. It turns out that the viscosity of an accretionary disk is not the same everywhere throughout the accretionary disk. Worse, it can vary with time. Why? I told you that friction between gas and dust in the accretionary disk is what causes its viscosity. It's more complicated than that. It turns out that viscosity is also related to turbulence. There we go. Just so that you believe me, there's actually an equation that relates viscosity to turbulence. I don't understand that equation. I'm not expecting you to either. I'm just telling you that there is one. And this is what it's derived from. Now, that turbulence in an accretionary disk, it turns out, is related to something called a magneto-rotational instability, which is a big fancy language meaning localized rotation of magnetic fields. You've seen localized rotation of magnetic fields if you look at the sun, for example, in H-alpha light. Actually, even if you look in white light and you look at sunspots. However, magnetic fields act on ionized particles, in other words, atoms that have lost or gained electrons and are charged as opposed to being neutral. And the commonest way to generate ionization in a disk around a young sun is by the action of solar radiation, light, especially ultraviolet light. But if parts of the accretionary disk are more opaque than others, then the solar radiation won't actually manage to penetrate those parts. The magneto-rotational instability will locally decrease, and so will the viscosity. Hence, the accretionary disk's viscosity will vary locally in space, and if the opacity, the opaqueness of the disk varies locally in time, then viscosity will vary locally in time as well. So what are we talking about here? How are planetary astrophysicists supposed to model the behavior and the structure of an accretionary disk and its influence over the accretion of dust, pebbles, planetesimals, planetary embryos, and eventually planets, if they can't even define the distribution of viscosity, drag, angular momentum, and migration in space and time? For a tangible everyday analog, imagine trying to make pancakes. I'm assuming you've all made pancakes. You're making pancakes when your batter has a spatially non-uniform viscosity that keeps changing on a 30-second time scale. Now, this headache has led some scientists to consider that this magneto-rotational instability business and its influence over viscosity is something for the ideal world. In other words, it's nothing but a mathematical model that wouldn't actually exist in the real world because it would be suppressed by something called magnetohydrodynamic effects. I have no idea what they are, but that's what we are told. And so, of course, they will look to find other ways of modeling. Remember, the only reason that we've been discussing viscosity at all is because it's been invoked by mainstream scientists. This isn't off-the-wall minority science. This is mainstream stuff, as the primary agent for the transfer of angular momentum that then allows the migration of gas, dust, and particles towards the sun, thereby controlling their ability to accrete to each other. But what if there was another way of transferring angular momentum? Then we could leave viscosity, turbulence, and all those complicated things, we could leave them out of the modeling altogether. Hence, as I said at the beginning, there's a school of thought that invokes various disk winds, either a solar wind or a wind generated by the heat of the accretionary disk itself, to transfer angular momentum. Now, I'm assuming they mean that the angular momentum is carried away by the winds themselves. But we're not out of the woods yet. There's yet another school of thought that suggests that turbulence, and hence viscosity, can be generated by mechanical instabilities. Remember the idea I mentioned earlier of particles drifting? I shouldn't do that. Come on. There, drifting from the disk surface in towards the midplane, and in so doing generating spontaneous turbulence by forcing midplane gas to rotate faster than the gas out near the surfaces of the accretionary disk, and thereby influencing angular momentum of gas or particle migration. That's the kind of thing that they're getting at here. I did warn you that there were multiple schools of thought and that nothing was black and white. when it comes to the early solar system. Okay, so where have we come to? Let's recap. First, there is a seductive model of planetary migration, which tries to explain the origins of the planetary component of our solar system. But seductive or not, it has major gaps. What happened between the first 100 million years after the formation of the Sun and the supposed late heavy bombardment 600 million years later? We'll examine this planetary model, migration model, and the late heavy bombardment in a later talk. But for now, the take-home message is that planetary astrophysicists are currently questioning when planetary migration happened. Did it actually happen at 600 million years after the formation of the Sun? And they're questioning whether there was a late heavy bombardment at all. Second, the accretionary model from dust to planets sounds good, but it's full of poorly understood steps, including multiple barriers that must be overcome before it really makes sense in any of the models that they're trying to generate. And the take-home message here is that planetary astrophysicists have been making enormous progress in terms of modeling, but that little of this has leaked into the amateur literature. And you saw how it is that they're having to confront all kinds of issues. We'll take a look at this too in yet another talk. It's absolutely fascinating, by the way. And third, the behavior of the gas, dust, and solid particles of all sizes, and hence their accretion in the protoplanetary disk around the early Sun, was all governed essentially by the viscosity of that disk. The take-home message here is that we have no way of knowing how that viscosity structure was distributed in space or how it evolved in time. So large-scale models of accretionary disk behavior and structure are dramatically oversimplified. The beginnings of the accretionary process are poorly understood, and it's something we're just going to have to live with because we're not going to get direct observations of what happened 4.5 billion years ago. Whatever. So next time Oscar invites me to this podium, we'll take a good look at the standard model of dust accretion first to form chondrules and then to form planets. It's wrong, by the way, and I'll tell you all about why. Thanks for listening.
All right, up next we've got our observation reports. So if those of you presenting observations can queue up to the side of the stage here and just be ready to come up and turn here. All right, Gordon Lewis is up first.
So last month, Oscar threw out a couple of challenges, and I decided to go and try and get them. So the first one, beginners, I think, was M3. So M3 is a globular cluster in Canis Venatici. It was the first thing that Messier discovered, but it's number 3. Don't know why. Its apparent magnitude is 6.2. There's about 500,000 stars here, and it's 33,900 light years away. And so I went out about 4 days after the meeting to Moose Creek, and this is, I think, a stack of about 6 frames on my DSLR on the back of my 6-inch Celestron. So the next one was the antenna galaxies, and that was the intermediate level. So NGC 4038 and 4039. These are a pair of interacting galaxies in Corvus, and they were discovered by Herschel in 1785. They're very dim objects, about 11.2 and 11.1. They're far away, they're about 45 million light years. So this is the future of the Milky Way and Andromeda when they start to interact. There are 2 gaseous antennas that come off and make it look like a bug's head. But I just couldn't get enough imagery. I need longer exposures. I need a different type of camera as opposed to my DSLR. But I'm still very happy with this. The last one was a nebula of opportunity, as I call it. It was at the FLO a couple of weeks ago. This is M27, the Dumbbell Nebula. It's the first planetary nebula discovered by Messier in 1764. It's a faint fuzzy at 7.5 magnitude, and it's about 1,300, a little more than 1,300 light years away. And the central white dwarf, where's the little dot? That's the dot, I believe that's the central white dwarf, is actually one of the larger known white dwarfs that are out there. So, not stars, but when I was in Florida at the end of March and beginning of April, I went and I saw the Falcon 9 launch that was on the 2nd of April that was taking a Dragon capsule, which had a payload for the International Space Station. There's a spot that I've gone to a couple of times now that you can see all the launch facilities. You don't have to pay to get to it. There's a group that goes there and they set up speakers and displays, and they broadcast the launch audio. And you can get some excellent, excellent photos. These are just a couple of photos that I've got. And if you're, I've got 3 photos apparently. And so it's very impressive. The sound takes like 20 or 30 seconds to hit you because you're about 10 miles away. And so if you're interested in going, this is where they launch from. This is a highway that goes across the Banana River, which is the body of water here. There's a spot on the east side, on the northeast side of one of the ends of the bridges, where you can pull off the road and you'll find either it'll be like a mobile home or it'll be a bunch of amateur radio operators who set up, and they run they've been doing this since the moon. They've been launching people to the moon. There's some coordinates here. If you go to this website, they have some information. They don't charge anything, and they'll even give you a little certificate if you send them an email. That's it for me.
What do you mean by what 3 words at the bottom?
So what 3 words? Okay, so what 3 words is another way, instead of having to put in big long things like that, you can get an app called What 3 Words, and they've broken the world down into about I think they're 10-meter grids. Every grid has 3 words, 3 common words, so that you can say, well, I live at Laughed Robotic Bluntly, as opposed to, follow these instructions and hope you get there. They're used often in places in developing parts of the world where they don't really have a good road network or a good addressing system. It's just another way. It's another way of naming waypoints.
All right, Bob.
Which one is this? Gotcha.
We were given Able 33 to look at, and I really appreciate that one. It's setting in the west into the sun. So you get about 20 minutes before the sun goes down, and then it goes down. And then the moon came right across this field. So this was a nightmare to image. But it's still fascinating. It's about 2,700 light years away. It's a globular, it's a exploded star. It's a planetary. And the star is actually visible by naked eye at just a little under magnitude 6. And it's about 1/3 the way toward this. And it's 3 times as bright as our sun in actual fact. This object deserves a ton more time. I'm going to catch it maybe next year when it's coming up in the west instead and get all night on it instead of a few minutes a day. Fascinating object. It's bright, bright blue. This is Hickson 44 from our previous images, and just a really interesting collection of galaxies. They're about 50 million light years away, I believe. No, not yet. I think that's 100 million light years away. And there's the names of them. Kind of an interesting collection of a whole bunch of different kinds of galaxies all at once in one image. Ring Nebula, this is a terrible picture with the moon coming across in the sky. It's a little blown out. There's an area around it, I don't think it shows up in this picture, probably 3 times as big as that, where the red actually extends out into it. So this is the planetary too, where the star blew up and spread out this ball of gas that's being lit up by the neutron star, the white dwarf in the very middle. The white dwarf, I think, is about 18 magnitude, so it's pretty hard to see visually. This is M3. We heard a very good description of M3 already. It's one of the things about those, it's got about 275 variable stars in there. If you watch carefully, you'll see them actually moving a little bit. Once the pot laws change, you'll see it better. This is the antenna galaxy, and this was 2 spiral galaxies that collided, and they think it's going to turn into an elliptical galaxy in 200 million years. Pretty wild collision. And is that it? That's it. Thank you.
Well, I've got something for you tonight you might not have run into before. Has anybody ever seen a conundrum? I think I have one for you. Which one am I pushing here?
The arrow that points to the right.
Okay, so Bob just showed us a photograph of Hickson 44. I tried to do a sketch of it from my backyard in Orleans with my 12-inch dial. And I've got 4 galaxies there, but only 2 of them are anywhere near the right place. But this is what I saw, it really is. The top button is the pointer?
Yeah.
So I think this one is right, and this one is right. The third one should be there, and the one with the curly Q's on the end should be, I'm not sure my mirror orientation, either there or there. What this is, and what this is, I don't know. I think it's averted imagination. It's a galaxy cluster, there have got to be more than 2, right? Exactly. It could be I discovered 2 comets. That's possible. Highly unlikely.
You know, Gordon, the pot laws don't change till July.
No?
No.
Okay. It could be internal reflection. There are a lot of streetlights nearby, although they weren't really visible. The leaves were starting to come out then, so it shouldn't have been too bad. So I have no idea what it is, but that is an accurate representation of what I was seeing. So there you go, a conundrum. Another galaxy group. This one was done at the FLO Star Party on the 12th. And again, with my 12-inch dial. This is NGC 4278, which is this one. And then 4283 is there. And then this little guy is 4286. I can't read my notes here, so I can't tell you the magnitudes, but I think they're around 12 to 13 and a half, something like that. And then last one, it's one of my favorite asterisms. Has anybody seen this one before? The Stargate? No? Anyway, it's just, I think we have a slide, I'll show you the position of it. But it's just, triangle within triangle. And it looks like the Stargate from some science fiction thing. It's located in Corvus. All right, now it's not moving. There we go. Okay, so you've got the Sombrero Galaxy here, and Sombrero Galaxy's neat. Has anybody ever seen the arrow that points straight at the Sombrero? Anyway, it's just below, if you're looking at the star chart, not necessarily in your telescope, just below that arrow. So, that's all I have for you. Thank you.
You're next.
I think you're pulling a fast one on me. Why do I get that feeling? Because I know you. All right. All right, well, hi, everybody. I get my orientation here on pointer. Oh, I am next. Huh? Yeah, how about that?
I screwed up the slide with the list.
You did, okay, cool. So a couple of months ago, I showed you this particular image. This is the Cone Nebula and the Christmas tree cluster in Monoceros, and it's a very attractive object there. The constellation itself, the unicorn itself, is not very conspicuous. It's a collection of like fourth magnitude stars and that, but it does contain some really cool objects, like this grouping and the Rosette Nebula, for instance. But there's other objects in there, and that's what I want to share with you tonight, especially one in particular. So let's see if I can get this button to work. There we go. And the pointer.
The button just above the arrows.
I can see why people have difficulties with this. These are little buttons. So unfortunately, I didn't have a wider field view of this available. I didn't have time to take a wider field view there, but I just wanted to give you an idea of where these objects are that I'm talking about, in case you get a chance to get out under some dark skies and see them, because some of these are visible through a reasonable sized telescope and that, and others require imaging. So that's the area there that contains the Cone Nebula and the Christmas tree cluster, and also the other object that I want to share with you tonight. So you can see Monoceros is just underneath Gemini and Canis Major, the big dog. So good. Oh yes, you're right. Thank you. Good catch. Oh, you have beer. There you go. So what I've done with that, within that rectangle, I've superimposed the high resolution view I did of the Cone Nebula and the Christmas tree cluster. It lives up in that area. But the thing that's really kept me busy in this area is, if I can find the button, that guy, Hubble's Variable Nebula. It's in the same ballpark, and I've actually been imaging this for about the last 5 months, and you'll see why in a moment. So Hubble's Variable Nebula, just go ahead here. Hubble's Variable Nebula is an interesting object. I'll go back to the other one there. You can see with respect to the other image that I showed you there that it's quite small. It's very small. In fact, it's only about 2 arc minutes by about an arc minute and a half in size. It's a reflection nebula. It's about the size of the ring nebula that Bob just showed there. So for those of you that have seen that through a telescope there, you know about the size that I'm talking about. But this is a fascinating and actually well-studied object. And there's I think, Simon, you may find this particular interesting given your talk tonight. This is it's a bit of an enigmatic object, and stuff happens there. Hubble's Variable Nebula was discovered in 1783 by William Herschel, but it was the astronomer Edwin Hubble, who it's named after, and who the Hubble telescope is named after, that did the first serious in-depth studies of it back in the early part of the 20th century, around 1916 or so. And what he found was that this nebula, I'll go to that next slide now. This nebula varies in brightness in a short period of time. In fact, what he found was that this nebula can vary in the course of just a few months. Really fascinating object there. And so he and other contemporary astronomers photographed it and did detailed studies of it. And it really wasn't until relatively recently, in the last 3 or 4 decades, that we sort of come to start piecing together what's going on, what actually makes this nebula variable. So I've got a couple things to show you about this, because I was fascinated by this nebula. So this obviously is a Hubble Space Telescope image of that nebula superimposed on my background image. And so the first thing I want to show you is a bit of a time lapse. Okay, this image by the Hubble was taken in 1999, and my background image was just taken in the last few months. So we're talking about a 19-year span of time. So have an eye to that star. I'm gonna advance this now, and so I'll make the Hubble image disappear, and you'll see my background and you'll see my image of the nebula. Obviously not with the same resolution as the Hubble, but watch that star. See how that moves? Mm-hmm. So what you're seeing is 19 years of proper motion of that star as it moves through our galaxy there. It has a fairly high motion with respect to our line of sight there. And so, yeah, it's rather cool that you can see that. So that's 19 years. But that's not what's interesting about this nebula. This nebula, as Edwin Hubble discovered, varies in time. And as he said, it can vary over the course of just a few months. Well, to understand what this is, what you're looking at is a very, it's a complex structure. It's kind of like two parabolical shells of gas, kind of like two funnels back to back at an angle like this. And what you're seeing, the fan shape that you're seeing in front, you can just see a hint of the other parabolic shell and behind the bright tip there. It's kind of like a fan shape like this. And what Hubble and other astronomers discovered is that the brightness of this thing and the form of this thing can vary in time. So it begs the question, what's happening in this? Like, what's causing that variation? Because that fan that you're seeing is over a light year long. It's about 1.5 light years long, about a light year wide. So it's a good sized structure, and we're talking about fairly short-term fluctuations. Let me get this right here. So what's happening, the current theory, the current thoughts of this, and this has been backed up by some deep infrared photography of that bright part. That bright part, think of a comet. Okay, think of a comet. There's a very bright star in that. It's a B-class star, about 10 times the mass of the sun, so it's hot and it's burning at a good rate. It also has a companion star, a very active T-Tauri star in close orbit around it. And these are young stars. This system is estimated to be only about 300,000 years old. So this is a newly born star. So to your point, Simon, interesting that your talk was in my point of view is related to this. What we believe is happening in the tip of that structure, and again I'll just point that out in case you're not with me there. We can't actually see the star because it is shrouded by a really dense cloud of gas and dust. So, and it's lighting up that entire tip of that part of the funnel, if you will. But at the inner side of that, inside that area that we can't see, it's trying to image the nucleus of a comet, right? What we believe, and what has been shown through the studies, is that there's an accretion disk about 100 astronomical units in radius, so about 2.5 times the size of Pluto's orbit. And again, as I say, it goes to your point, Simon, about the age of when these various events happen. This disk, again, is 300,000 years old or so, and yet there are thick clouds of material in tight orbit around that binary star at the center of that, and it's blocking out some of the light of that bright star from reaching the outer part of the nebula. It's effectively, those dense clouds of dust are actually casting shadows on that much larger structure, which is the fan shape that I showed you. So to demonstrate, I'm going to get a little demo here in case you're wondering what I'm battling about. Go to demo. I got to do a demo, right? So anybody have an idea what that is? Can't see it? That's okay. Can't see the star there anyway. I'll help you out with this one. No, don't cheat. I've got my own sun. Kill those lights. There you go. Any idea? Here, I'll help a little bit. Why are you laughing? What is it? It's actually an Apollo astronaut. But you could see that, right? You couldn't see it before. That's what's happening around NGC 2261, Hubble's Variable Nebula, is that there are these clumps in orbit around the star that are actually opaque enough to block out the light and cast shadows on the nebula. So I was fascinated by the idea of being able to see a variation that's related to some early planetary formation 2,500 light years from here. Like, you know, that's pretty amazing if you can actually witness something like that. And so what I did is, for 5 months, I imaged that nebula with the 11-inch telescope and Canon 60DA to see just what Hubble was talking about when he talked about variations. I was thinking that, you know, there's going to be brightness variations, maybe a bit of morphing in the dark stuff, but what I observed was way beyond my expectations. So I'm going to show this to you. This time lapse spans 5 months, started in November, just finished in April, and it's 20 frames. I imaged this over the course of about 150 days, about 20 times. So on average, about eight days between frames. And unlike the type of imaging that I usually do, where I can spend, you know, several sessions and accumulate lots of good data and chuck away the bad stuff, this is like imaging a comet, because it changes. What I found was not on the order of months, not even weeks. This thing changes on the order of days. Its shape. So I'm going to show you this time lapse. Don't blink too much because it's really short. It's only 20 frames, and at the frame rate I'm running, it runs for about 3.5 seconds or so. Don't worry, I'll loop it a few times there. And before I show it to you, I want to thank Oscar, because I mentioned this to him last fall, that I was going to try to bag this thing. He very nicely offered to add some images to my collection there. So on a couple of nights there where he was out imaging his own stuff, he's running the same equipment that I am. He shot this for me as well and allowed me to use that data in my project here. So he contributed a couple of nights of imaging out of this collection. So thanks again, Oscar. That was much appreciated. Certainly it helped me out to add the collection there, because this, I had to shoot this when I could get it, right? I mean, I was trying to look at a progression. So even on cruddy nights, I was out there imaging that, even with the moon up. So you'll see that there's some variation in the quality of images from one to the other, some flickering of the stars, because some of the nights were just god awful, but it's a progression. And well, I'll show it to you. It'll loop a few times. And here we go.
Oh, wow.
That's crazy, eh? I particularly like, watch these two guys here.
It's moving at tremendous speed.
It is moving at tremendous speed.
That's fantastic.
And what I found is when I rendered this nebula, this video, I found that if I ran it backwards too, I would perceive it in a somewhat different way. And yes, I know the pop laws changed in July. Right? I'm good with that. But so what I've done is I've created another sequence showing this bunch, and also in reverse, and it'll loop a few times so you can see for yourself. It'll go backwards, and you'll see there's a bit of a break in between. And then it'll reverse, and you can see how these things move, especially those two dark round guys. So remember, this is about 8 days between frames there, so I was really just blown away with that. I was not expecting this magnitude of change on that kind of a time scale. And especially when as I say, when I see these two dark guys up here. No, I don't think they're protoplanets, Simon, but there's something dense blocking out that sunlight, and you can see the motion. You can just see the motion there. I wish I could image this over the course of a year, or have access to the Hubble Space Telescope without the atmospheric distortion, because I just find this fascinating. What you're seeing here is evidence of the very initial phase of the birth of a new planetary system, probably. With that accretion disk circulating around, blocking the shadows, blocking the starlight from reaching the outer part of the nebula there. I think what you're seeing is the very beginning, the very genesis of a new system of stars and planets. And again, this is only 300,000 years old, so food for thought. Hubble's Variable Nebula, aptly named, and yeah, certainly a lot of food for thought. Sorry, what? Huh? Okay, thank you very much.
Hi everyone. So this is a picture that I've been working on now for a couple of years actually. It just so happens that by the end of the first season that I took it, back in 2016, I lost it to, I tend to image only above a certain angle above the horizon, so this went too low to be able to get it. So it took, how do I say this here? Tongue twisted. So if an image goes down below too far down the horizon, you just basically wait till the next season to start capturing it again. And so this is 10 hours worth of exposure of the Iris Nebula. And I thought I'd just read you something off of my website about what this actually is. So this is NGC 7023 is a splendid example of an open star cluster associated with a reflection nebula. It was first observed in 1794 by William Herschel, and it lies in the constellation of Cepheus, 1,400 light years away. It's situated in the night sky 3.5 degrees southwest of Beta Cepheus. It is sometimes referred to as the Iris Nebula because of its resemblance to the flower of an iris. The nebula has a visual magnitude of 7.19 and is illuminated by a magnitude 6.8 star, which is cataloged SAO 19158. NGC 7023 lies in a region of the Milky Way which is darkened by dust. At its center is a very hot young star. It radiates invisible ultraviolet light, which some of the surrounding dusty cosmic filaments convert to visible red light in a process known as photoluminescence. Interestingly, the dominant color of the Iris Nebula is not red, but rather blue. This is characteristic of dust grains reflecting starlight. The dominant blue color, then, is evidence of dark, obscuring clouds of dust and molecular gas. The convoluted shapes of these clouds leads the eye to perceive the fantastic shape of the iris flower. Observations done in the infrared part of the spectrum, though, have indicated the possibility that the Iris Nebula may contain complex carbon molecules known as PAHs, which stands for polycyclic aromatic hydrocarbons. Directly to the west of the Iris Nebula, in a dark region above the petal structure of the iris, lies an open cluster associated with NGC 7023. It is cataloged as Colander 427, which is this little region right in here. So what I found fascinating about this one right here is that when you first image this thing, it's evident that there's definitely some dust all around the surrounding areas. But in the image processing of it, you can go down the rabbit hole, an infinite amount of layers. This took 24 hours worth of processing time, like actual processing time. And in that, in enhancing some of the dark structure there, you can sort of start to see these little filaments in here. So this, like I said, it took me a while to capture this. There's a lot of sub-exposures I ended up actually throwing out. I threw out, this is just the red, green, and blue. I threw out a lot of my luminance channel, just because, like as Paul says, on certain nights that the conditions are not as favorable, and then afterwards when you're looking at it, when I processed the red, green, and blue, it actually ended up being higher quality than my luminance channel. So in the future, I might go back and recapture some of that luminous channel and try to make this, even better that way. But it was a project in that I used PixInsight to process all these images, and until I processed this image, I thought that I knew a lot about processing in PixInsight. With this right here, it's like my world of knowledge of processing pictures just exploded into 10 times the amount. And I kind of got the motivation. I've been talking to Oscar about this. Given that we've been doing these imaging corner sessions here, that I might start to do some sessions based on processing using PixInsight, because a lot of people are familiar with Photoshop. PixInsight is not necessarily a new software on the scene, but it's gotten to the point now where it can pretty much replace Photoshop. It's an all-encompassing software where you can go right from the point of capturing your images using the telescope to using only PixInsight to put together all the pictures to its final product. And like I said, the rabbit hole goes so deep. It's unbelievable how many different ways you can come to the same end solution. It's particularly powerful for noise reduction. So I'm going to start doing some imaging corner sessions based on how to use this program in the future. And no time lapse for me tonight. Although I've got about probably about 40 time lapses I can show you guys now. I went down to the Southwest last fall, so I'm going to start showing those pretty soon as well too. I guess I'm being kicked off the stage. Thank you.
Alright, so I've got one to show. Jupiter was at opposition on May 8th. The seeing wasn't great when I was imaging it, but yeah, there's Jupiter. You got your great red spot and Io just off to the corner there. So that was shot with my 11-inch Edge HD and a NextImage 5. All right, now it's time for this month's Observing Challenge. We'll start with our beginner challenge, which will be the Lagoon Nebula. It's probably a little bit early for the Lagoon Nebula, so maybe later in the month it'll be up a little bit higher, but I just thought I'd throw that one in there to welcome summer in. So the Lagoon Nebula is an emission nebula in the constellation Sagittarius, also known as NGC 6523. So you see that it's just above the teapot of Sagittarius there. For our intermediate challenge, I've thrown out the Cat's Eye Nebula in the constellation Draco. It's cataloged as NGC 6543. It's a planetary nebula, magnitude 8.1, with a central star of magnitude 10.9. For our advanced challenges, it's Seyfert's Sextet. It's also known as Pixton Compact Galaxy Group 79. It's a tight gathering of galaxies in the northern corner of Serpens. It's cataloged as NGC 6027 and NGC 6027A through E. So there's 6 in there. All right. For our lunar challenge, Schroeder's Valley, which is located in Oceanus Procellarum. It's named for the German selenographer Johannes Schroeder. So it originates at a crater near Herodotus, and it's 185 kilometers long, 10 kilometers at its widest, and 400 meters at its thinnest. So I want to see people start submitting more stuff for the Observers Challenge, both to astronauts, to Gordon, and for the meeting. That'd be great. And yeah, let's hope for some clear skies so that we can tackle these challenges.
Oscar, it's worth pointing out that Schroeder's Valley could not have been carved by water, obviously, so it was carved by lava.
Thank you, Simon.
It must have been one hell of a sight to see when it was happening.
All right, FLO star parties. So we had one on May 12th. The weather was cooperative. The next one is June 9th. We'll have a waning crescent moon. So you can see all future star parties at that website there. They all take place in the parking lot of the CARP library, right next to the Deacon bunker. All right, Ottawa Astronomy Workshop Series. So the next one is June 7th. Glenn LeDrew will be giving a talk on stellar associations. So contact Jim Thompson to reserve a spot. Public star party dates. So we've got the next one being June 8th with a couple backup rain dates and a members only FLO star party on the 9th of June.
A week today.
A week today. On Friday, July 6th and Saturday, July 7th, we'll be having a public star party at the Cube Gallery in Westboro. So we need some volunteers. Please talk to Mike Mugdant. He's organizing that. We'll need folks to set up telescopes and work with the public. All right, so there's a Dark Sky Festival, August 23rd to 26th. At the Dark Sky Preserve called Wood Buffalo National Park in the Northwest Territories. There's more information available at their website there. Estelle's Pick of the Month, Astronomy Photographer of the Year. So you can see Estelle after the meeting to access Boatstone's library. Here are the folks that help run the club. And on June 23rd will be Eric Fiala's burial. You'll recall that he was a member of the club. He was the videographer for many of our meetings and was quite involved in other things in the club. Yeah, so I guess there will be snacks at Eunice's home afterwards. So you can talk to, who can we talk to for information? You can talk to Gordon for more information.
Yeah, just email.
Or email Gordon. Recordings of the meetings are available on our website. Okay, tonight's audience 77. Thank you for coming. We'll have our post meeting at Grace O'Malley's again. And our next meeting is July 6th hope to see you there. And if you have any ideas for talks, please send me an email. So as always, we got some benefits of being a member of the club: access to the Tedman Library, the STEM Mock Library, the FLO, various publications. And now it's time for door prizes.